Hi everyone, welcome. Welcome to this course. So far we have studied the random walks and Brownian motions. So today uh, I will discuss some problems, real life problems that is totally involving random motions or random walks, and we will try to solve those problems and using the random walks. So basically we will give some situations and we will see how the biased random walks produces results, and how unbiased random walks, whether the forward probability and backward probability is not equal, that will have some consequences. Okay, so let's start then. Let me share my screen. Yeah, yes. So basically we will discuss some problems. So some problems regarding random walk, and we will see specifically few problems, and we will see how this tool will be useful to sort of address few real life problems. Okay, so let's first assume that there is a guy Lux. So the Lux a boy Lux, he is on an island. Okay, and this is a fair big island. Let's say this is an island, and at these two ends there is cliff, so he can fall up to this cliff. We call it cliff of doom, and there is another fall here. This is called pit of disaster. Okay, so in between there are, it can take few steps. Okay, so okay, so this is, let's say this is 0, and let's say Lux is at a position N, and this is at W. So let's name this problem as Lux on a big island. Okay, so basically we'll see that he is n inches away, so it can take 1 inch step towards, let's say 1 foot steps uh, forward, right and left. Okay, so Lux starts, or he is at, Lux is at a place n feet away from cliff of doom. Okay, and he is also W feet away there is a W feet away from the feet up disaster. Okay. So basically Lux starts at position in, and he is he is intoxicated. He can just take one step right and one step left, and his random walk stops when he reaches 0 or W, and basically n is less or equal to W, right? Okay, so there are three possibilities, right? First possibility, he can fall off the cliff of doom. Just fall to the cliff of doom. B, he can fall into the pit of disaster. Or he can hop around the island forever. Of course, if he is lucky. We'll see whether he is lucky or not. So let's say we can check what will be the probabilities associated with those things. Let's say Rn is the probability that Lux falls to the right into pit of disaster. Okay, so he just falls into this. Okay, after given that given that he starts from position in, so let's say he can take n feet, 1 feet per, so one step equal to 1 feet, and W is very long, okay, large. Okay, so let's say if he if he starts at W, he fall into the position, he falls into the pit immediately, because he is that position, right? So he will be, so then it will be Rw is equal to 1. So but if he starts from 0, that means he is in cliff of doom. So then if he starts at 0, then r0 equal to, so this n is denoted by this starting point. Okay, let's say, but let's say if he starts in between region, let's say 0, in between 0 and w. Okay, then we can break his feet, or we can analyze that how he will move, how his feet how his fate will be determined. Okay, so basically what we'll do, so we can break into, we can break the analysis of his fate of his fate into two cases. On the direction of his first hop or first step. What is this? What are those? First, his first step is towards left. That means he is at position n minus 1. So this is, he was at like this. So this is n minus 1, this is n, right? And eventually he falls into the pit of disaster with a probability r n minus 1. Okay, and the second case is first step towards right. That means n, and he will be at n plus 1 position. So eventually falls into the pit of disaster with a probability r n plus 1. Okay, so from here we can get what will be the total probability. So total probability of falling into the pit of disaster, that is in the right fall, will be, starting from n, is r n plus 1 plus r n minus 1, and happening, this is the probability, but there is an 50% chance of taking first step in the right direction and 50% chance of taking the first step in uh, left direction. So that's why this is half. So let's say this is equation number 1. Now how can we solve this recursion relation? Because it is important to solve this recursion relation. So basically, if 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 n equal to 0, if n equal to 0, that means initially our probability was Rn, if Rw is equal to 1, and if it starts from 0, the probability is 0. So, and we are also getting Rn is equal to half Rn minus 1 plus half Rn plus 1, where n is in this between this region. Okay, so this is a linear recurrence. Okay, so in a normal recurrence, Rn is written as a function of preceding terms, right? What will be the preceding terms? So here, but here Rn is a uh, function of two terms. This is a preceding term, like if it is in these things, and there is a following term. I am just talking about the positions, right? This is Rn. Okay, so you can rearrange this thing from like this. You can rearrange like this, Rn plus 1 as 2Rn minus Rn minus 1, right? So this is the characteristic equations we can write as, if you take this, let's say this is x, this will be x squared. You can solve it like this, x squared minus 2x plus 1, taking okay. So like this is like starting from this and you're multiplying the probability. So now this equation has a 2 as a double root, right? So solving these equations, you can get this equation has a double root of x is equal to 1, and there is no inhomogeneous part. So since there is no inhomogeneous part, so the general solution, so the general solution will become Rn is equal to a to the power a into 1 to the power n plus b into 1 to the power n in times n, that is a times bn. Now there is a boundary conditions of with now there is also boundary conditions. Let's say this is 2, and the boundary conditions that R0 was 0 and Rw was 1. So if you substitute this, R0 means n equal to 0. If you substitute this Rn is equal to 0, A is there and B times n equal to 0. So from here you get A is equal to 0, right? Similarly, R W is equal to 1, so this is 1 is equal to A plus B W, like this, and equal to 0. So from here you can get B W is equal to 1, that gives you B is equal to 1 by W. So from here you can get A is equal to 0 and B is equal to 1 by W. So from here we can get the solution of the recurrence relation like this, that R n is n by W. So you can get Rn is n by W. So this is equation number 3. So from our analysis, what we can say, that from our analysis we can say, if lux starts in fit from the left side of an island which is W feet across, then he falls off the right side, with probability n by W. So that means how much it is away from, if it is away from the left side is more, then the probability of falling to the right side is more, which makes sense, right? Now we can calculate, let's compute the probability that he falls off the left side by using the symmetry of the problem. Now if you see the symmetry of the problem, that if it is starting at a position n, then he will falls off in the same probability. Let's say if it starts at position W minus n, which will be W minus n by n. So what I tried to mean is, the probability that he falls off the left side starting at n is the same as the probability that he falls off the right side starting at position w minus n, which is w minus n by n. So what I mean by this, let's say this is 0 and this is w. Let's say starting from this and to get to falling here is same as, so this is n, this is w minus n, so is same as, if it is starting from w minus n then and falling to this, then this position will be n. This is like symmetry, right? Now this is then the bad news, right? Then total probability of falling to the either side is equal to 1. So this is extremely bad. Why? So probability that lux eventually falls off one side or the other, one side or the other, is n by w plus w minus n by w, that makes it 1, right? So this is very grim because there is no probability, there is no hope that he will sort of survive. Okay, so then what we are getting here, that probability that lux hops around on the island and possibly enjoying the sunsets is 0. So this is very grim. So eventually, that where if you say that it's an infinite plateau, there also the probability eventually he, let's say this is an infinite plateau, then there is a probability 1 that it will fall to this pit of disasters. So now, so let's see that what are the missing points here. So let's say what is the life expectancy of this. Let's say the life expectancy of lux. So let's say it may happen that eventually he will fall off, but there will be some time before falling off that he will hop around, right? So lux may get to hop around or roam around for a while before he goes over an edge, right? So let's use the same setup at these things, right? So let assume xn is lux expected lifespan, which is measured in number of steps, measured in number of steps. So if it starts at either age, then he will die immediately, right? Because on either age their death is sort of waving him eventually. So if he starts at either age of this island, then he dies immediately. That makes it x0 is equal to 0 and xw is equal to 0. That means lifespan if it starts from w and 0. Let if he somehow starts in the middle, starts in the middle, let's say 0 in w, in between, then we can break down this analysis in two steps, right? First, if his first step towards left, then he reaches to n minus 1, because this is n, left will be n minus 1, this is n, right? Then we can expect to live for at least another xn minus 1 positions. Similarly, if his first hop towards right, then he reaches to n plus 1. That means it starts from here, then this is n plus 1, this is n, right? So then one can expect it will live for another. So see how this random walk will be connected, huh? So then what will be the total expectation? So law of total expectation, we can then write that expectancy of its living is half of xn minus 1 plus half of xn plus 1. So let's say this is equation number 4. Okay, so let's solve this recurrence relation. Okay, so now it will be, so let's let's write its initial conditions. Then x0 starting from 0 is 0, and if starts from at w positions, that will also be 0, because at those two ends it will never leave. Okay, and xn, then it will be 1 plus half xn minus 1 plus xn plus 1. Okay, so sorry, there will be 1 because it is leaving one step in n, because you have to take one step, right? So this is the relation. Okay, so now if you can rewrite this equation again, you can rewrite this, then because we can write it as in a forward equations, then this will be 2xn minus xn minus 1 minus 2. So this is one recurrence relations. So those are the characteristic equation. This is kind of a difference equation. So this will be x squared is equal to 2x minus 1. Okay, so from here you can write x square minus 2x plus 1 equal to 0. Okay, okay, so basically what we are doing here, we are getting the same characteristic equations, and from here we will get same root xn will be a plus bn. But here this is different from the previous thing because there is an inhomogeneous term. So this time this is different from the previous equation. Why? Because there is an inhomogeneous term. Okay, and this term is this term is an constant, right? Because you can get the difference like this. So let's say we can try a solution first. X is n is equal to c, and if it is not successful, then we can try a solution xn is equal to c plus dn. Then the higher term c plus dn plus en squared. Okay, so we can try different things out, and so we can see if you try those things, these two will not work out, but this sort of works out. Okay, so putting these two in these equations, you can get that c plus d n plus 1 plus e n plus 1 whole squared is equal to 2 times c plus dn plus en squared minus c plus d n minus 1 plus e n minus 1 whole square minus 2. So if you solve it, then it becomes c to c and c cancels out. So c cancels out, dn plus 1 to dn, there is 1 minus dn, so 1 dn remains, and there is 1 plus d, so plus d. This is also cancels out, so only things remains this one, right? So e n plus 1 whole squared 2 e n squared minus e n minus 1 whole squared minus 2. So from here you can get e n plus 1 whole squared plus n minus 1 whole squared 2 en squared minus 2. So this is a plus b whole square plus a minus b the whole square, so this will 2a square plus b square, so this will be 2a square plus b square, like this. So this cancels out, so only thing remains 2e is equal to minus 2, that makes e is equal to minus 1. Okay, so from here you get this. So now we can write the solution as xn is equal to c plus dn minus n squared. So it's a particular solution for all values of c and d. Okay, so let's say for simplicity c is equal to d is equal to 0, then we can get a particular solution xn is equal to minus n squared. Okay, so adding these terms, then we can get also a plus bn minus n squared. So this is a particular solution, this is particular solution, and this is homogeneous solution that we calculated just few minutes back. Then we can get this. Now if you substitute the boundary condition x0 is equal to 0, that makes 0 is equal to a plus 0 minus 0, that makes a is equal to 0. Similarly xw is equal to 0, that also makes 0 a plus bw minus w square, and this is 0. So this is 0, so bw is equal to w square, that makes W is equal to B, or B is equal to W. So from here you can write this solution xn as Wn minus n squared, so n times W minus n. So you can get this solution of expectancy as n times W minus n. Now how can you interpret these solutions? Okay, so to interpret this solution, you need to take help following things. Okay, interpretations of the solution. Okay, okay, so you got to know that Lux expected lifespan becomes xn is equal to n times W minus n. So that is, actually if you see the product of the distance of the two edges, right? So let's say this is 0, this is W, it starts from this. So from this edge this distance is n, and from this edge this distance in W minus n. So this is the product of two edges. So you can get, let's say this. So this is very bright color, let me use them. So from here you can write that this is the product of the distances, to the two edges. Okay, that means if he is 4 feet away from the left edge and 8 feet away from right edge, then its expectancy will be 4 times 8, that means 32 steps. So which is like logical, right? So if it residing at the middle, that will be more, well, that will be maximum, right? So now let's make this problem a little bit interesting. Getting, let's say, now, so the maximum expectancy, first let's comment it out. Maximum expectancy, life expectancy, will be when it is equidistant from both edges. So let's take another thing. So where, let's say, Lux is in infinite plateau region. Okay, plateau region. Okay, so if it is at infinite plateau region, then let's say it has, let's say it has 1 feet left. It has the cliff 1 feet to his left. So let's say this is continue and it starts from 1 and this is 0. So he will can like falls into this thing. So so here his expected lifespan, then so if you use this thing, then it will be limit w tends to infinity, n is 1, w minus 1, so 1 times w minus 1. If w tends to infinity, then it becomes infinity. So here you can see, although there is probability that if it is like probability of 1 falling into the cliff, but its expectancy is infinity. So yes, lux is certain to eventually fall off the cliff of doom, but his expected lifespan lifespan is infinite. That means when it will happen, nobody knows, right? So now you will be puzzled. That first time you said that it will eventually fall to the left. There will be some probability 1, but why? And now you are saying that the expectancy is infinity. So sort of this is contradicting, right? So let's say, so so let's say what is it's changing here. Let's say the probability pk that lux falls from the cliff of doom on the kth step is, this is some theta function of 1 by k to the power 3 by 2. And if you integrate this thing, this actually converges, right? That means you can confirm that I equal to 1 to infinity 1 by k 3 by 2, it converges. Okay. Now expected time, which is written as I equal to 1 infinity kpk, that actually is greater than c, k is equal to 1 to infinity k by 3 by 2, that makes it c k equal to 1 infinity 1 by root k, 1 by root k, and that makes it infinity. So here c is constant, where c is constant, okay, which is embedded in this theta function. So from here you can say that the probability, which is the summation of this thing, that converges, but its expectation value, it is sort of blowing up. Okay, so that's sort of telling our answer. So it can happen that there are finite, or like that the sheer probability of falling up to these edges, but the expectancy may be more than that. Okay, so now let's apply this thing to the a game of gambling. Okay, so we all love to hear stories about gambling. Okay, now let's say applications to fair gambling. Okay, and nowadays there is so much interest about stock market. I'm not saying that this is stock market is gambling. I'm just telling that there are, like, if you think about it, if it is unbiased, then that will be 50% chance of going upward and 50% chance of going downward. But there is other factors, of course, that's why it's not fair. Let's say this poor chap Lux goes to a casino with, let's say, with n million rupees, in his pocket. Okay, now his plan is to make only $1 bet. Okay, and somehow he has found a casino that will offer her truly even odds. So truly even odds means there are 50% winning and 50% chance of losing. So chance of winning is half, and losing is also half. And he will play until his total n million money is gone. Okay, so he will play until he is broke, or he has owned some amount of money m. Okay, so if in this latter half he will go, when it is he winning some price, let's say this is not million, let's say some n amount of money, rupees. Okay, So he will go home with W is equal to n plus m rupees. Okay. So now let's calculate calculate what is the probability, what is the probability the probability that C goes sorry Lux Lux goes home a winner. Okay, so this is like the same thing. So this is like, this is 0 and this is W, same thing like the problem that we have just discussed, similar to this problem. So this is cliff of doom and this is pit of disaster, although this is not a disaster. Okay, so the gambler, so if you check this, so the gambler goes home broke with, broke means like if you are starting with n, you are like this probability, you know this probability, this is n by W. What is n? N is, W is n plus m, so this is n plus m. And gambler goes home a winner with a probability how much? W minus n, W minus n by W, which is n by n plus m. Earlier it was, so you can see, so n by W, so this will be m by, this will be m by, right. So you can see that of course the gambler goes home, because if you add those things that will be 1. Okay, and now if you see the number of bets, the number of bets before the gambler goes home is similar to the thing we just did, that how Lux was roaming around the valley. So it is similar to this, because it is roaming around the valley, that means it is, he is playing, right. The number of bets before the gambler goes home is same as n times W minus M, and that makes it Nm. Nm. So from here you can get some interesting ideas that if the gambler if the gambler gets greedy and and keeps playing until he is broke, because if he is broke nobody will be kinder to him to play broke, then that means at this region, this W, this will be going to infinite. That means this will be infinite problem. So similar to the problem we just discussed. So eventually we can say that the gambler the gambler eventually goes broke with certain probability, with probability 1. So if he is greedy and if he continues playing, he will be broke one at certain time. But but the number of bets before he goes broke he goes broke is expected to be infinite infinite. So from here you can get a nice message that in gambling, if you are ahead or if you win something, so stop playing. That will be your first mantra. Because if you are greedy, if you keep playing, then you will be everything will be ruined at some point of time. Okay. Okay, so the bottom line is here. The bottom line is, when gambling quit while you are ahead. So if you are ahead, please quit. And if you play until you go broke, you will go broke surely. You will go broke surely. Isn't it fascinating? Right. So that's the thing. But again, this is not the actual scenario, right? If you are in a casino, then the probability of winning and probability of losing is not same. Okay. Odds are always against us. So odds are always against. Now that is what happens. Like if you are very smart enough, like a mathematician, I'm forgetting his name. So a Russian mathematician probably. So he was so smart and he figured out how these casinos work and how are their odds, and he strategized some plans. and whenever he visited those casinos, he would win a lot, hell amount of money. So then the casino owners, they took notice of that facts, and they started banning him. So if you are good at it, you will get some idea about it, and you will make some strategy, and you will sort of make those casino owners broke. Okay. Now the real case, if it is unbiased random walk, if it is unbiased random walk. Okay. Let's say there is a, if you are choosing black and red Russian roulette, you are playing. So winning probability, let's say winning probability is around P, and losing it's Q, and P is less than Q. Okay. So basically, if you see that here, if you start from very close to half, then that is not so much problematic, but there is odds are much more against this. So let's find out the recurrence relations for this. So let's say we have that problem of the fate of lux. So let's approach the problem in the same way as lux, you know oh, okay. So we will approach it in the same way as lux was hopping or roaming in the valley or island. Okay, let's see. Okay, so same thing, C has, sorry, lux has in dollars, and so let's say lux has in rupees, not dollars, because now, and he is taking, and he is taking 1 rupee bet. So the packet size is 1 rupee. Okay, and the probability of winning is, the the probability of winning is P, and he plays until C of until he either goes bankrupt, or has W is equal to N plus M rupees in his pocket. In his pocket. So W is the total amount of money he ends up with. Okay, and M is the total amount of wealth you want to increase, right? Now our job is to calculate the probability Rn, which is that he goes home a winner. Okay, so let's first identify the boundary conditions for this problems. So what are those boundary conditions here? So if he starts with no money, then see, but then he cannot play, so he is bankrupt anybody at that point of time. So R0 means when n equal to 0, he is 0, cannot play. And let's say if he has this W amount of money, then also he will not play, but he will win, right? So that will making it 1. Now you differentiate this thing, or like differentiate this regime into two different things. First, like divide this analysis into two cases. Okay. So first, wins his first bet with probability P. Okay. If he has first bet, then he has n plus 1 rupees for the next this thing, right? And then he will have probability Rn plus 1 probability to reach W amount of money. Okay, that is one thing. Now let's say he loses he loses his first bet. Then, and what is the losing probability will be? 1 minus p, because winning probability is p. And then he will have n minus $1, because $1 he lost, sorry, rupees, let's say. And probability of r n minus 1 of reaching his aim, which is w amount of money. Okay, so now if you get these two probabilities, then you can get the total probability of its winning, or of its, like, reaching his goal. Okay, so that thing will be like, if you if you plug those things into total probability ability, then it gives Rn is equal to P Rn plus 1 plus 1 minus P Rn minus 1. So this is a recursion relation. We will solve this recursion relation. Okay. Okay. So we'll solve this recursion relation and to see that has. So remember what we are doing here. So basically what we have done is we analyze this, problem where there is a, land, he can sort of hop around this thing, and it has some finite width, and we saw first that what is the probability that he will reach this point, like he will fall into the pit of disaster. Now if it starts at this point, then the probability is 1, right? If it starts from this point, then there is no way he can reach here. That's why Rw is equal to 1 and R0 equal to 0, 1. And now we are getting that what will be the probability of n when it's in between. So then to calculate that, what we have done, we have, sort of uh, made two things into two steps. Okay, that, let's say its first step is towards left, then he will, if it is towards left, then he will be at position one step behind, n minus 1 positions. And if he takes some position right, then he will be at n plus 1 position, right? And the main thing was, so if at the next step he takes right step, then he will be at n plus 1 step. Okay, since the probability of going half, forward and backward is half, then the probability of falling into the pit is like probability of falling from at next step Rn plus 1 and half times probability of falling from Rn minus 1. This is kind of a recursion relation, right? And if you solve this recursion relation, then this is coming out to be like this. So you need to solve the difference equations. So here you can get, this is the general solutions with 1. That means it will be difference, it will be a plus bn, right? So from a plus bn you can get, let's say using the boundary conditions, that how let n equal to 0 and when n equal to 0, then r0 is 0. When n equal to w, that means it is right hand, that equal to 1, and from that point you get this, the probability. Okay, now after computing all these probabilities you will get these things. Now you can see that the probability of hop around is 0. So probability of going to either ends is adding to be 1. But if you see that what is the life expectancy, means what is the life expectancy of hopping, then we calculated that thing also, and we expected this probability is n times w minus n. That means if it starts at the middle point, then that expectancy is higher, and that is sort of expected. Let's say if it is at middle point, then there will be much more steps you will be spending in between. So now if you see, let's say if it starts from this end just one step away from the left cliff, then that lifespan is tends to infinity. Now it sounds bizarre that Lux is certain to eventually fall off the cliff, but the expected lifespan is infinity. But you can make sense if you assume the probability as a function of 1 by k to the power 3 by 2, where this function is converges but its expectation value is not converging. Okay, now we actually as sort of applied this thing to understand that how this fairing gambling games happens. So the situation is, it starts with a money in, and that guy, that fellow, stops playing the gambling when he wins n plus m amount of money or he goes broke. So this problem actually eventually becomes like this: 0 means he is broke, w, which is n plus m, that means he achieved his objective and he will quit. So you can see the similarities, and you can promptly write that the gambler goes home broke with probability. That means the probability of starting from here to here, that means n by w, this is n plus m, and probability of going this position is like the probability of going here, that is m by n plus m. So this is because what is the displacement size. So from here you can see that what is the number of bets before he can go home, that is in m. Okay, so that means if the gambler gets greedy and keeps playing until he's broke, that means gambler eventually will go broke, and probability with 1. And but the number of bets that is required to go broke, that is quite infinity. Now that means when you gambling, quit when you are ahead. That means if you win something, that is the point you should stop. But in real life, you know, gambling is unbiased. So there are more odds that is against you, and we talked about that this thing, and we got this recursion relation for this total probability of these things, and we will solve this recursion relation, and we will dive deep into this in the next class.